The future of transportation is moving rapidly toward autonomous vehicles, or self-driving cars. These vehicles rely on sensors, artificial intelligence, machine learning, and communication systems to operate with little or no human input. Autonomous vehicles are changing how we think about transportation. They offer a glimpse into a future where travel is safer, more efficient, and more accessible. This is a journey worth taking. This is part 2 of our series exploring the technology that's driving this revolution. We talked about the history and evolution of self-driving cars in our previous video, and now we'll dive deeper into how these vehicles work, their current status, and the challenges and opportunities that lie ahead. So buckle up and get ready for an exciting ride. Autonomous vehicles hold immense potential for transforming the future of transportation. These remarkable machines are engineered to navigate roads, highways, and urban environments without direct human intervention. At the core of their operation lies a sophisticated interplay of cutting-edge technologies working in harmony to ensure safety, efficiency, and reliability. Let us delve into the inner workings of autonomous vehicles and explore how they are redefining the boundaries of mobility. The primary motivation behind the development of autonomous vehicles is to enhance safety on our roads. Human error is responsible for more than 90% of road accidents, highlighting the potential for improvement in this domain. Autonomous vehicles are designed to perceive their understand traffic rules, and react swiftly and accurately, potentially reducing accidents and saving lives. Moreover, these vehicles offer a glimpse of a future where mobility becomes more accessible to individuals who are unable to drive, such as the elderly or those with disabilities. One of the key advantages of autonomous vehicles is their promise of efficiency. By optimizing routes, reducing traffic jams, and minimizing energy consumption, these vehicles can save time and resources. They can communicate with each other and infrastructure to coordinate movements, reducing congestion and travel time. Furthermore, autonomous vehicles have the potential to lower costs in logistics and ride-hailing services, making transportation more affordable and accessible. To understand how autonomous vehicles function, it's essential to examine the components that make up their intricate design. Perception forms the foundation upon which autonomous vehicles operate. It involves using various sensors such as LiDAR, radar, cameras, and ultrasonic sensors to collect data about the vehicles. LiDAR sensors use laser beams to measure distances, creating detailed maps of the environment. Radar systems utilize radio waves to detect objects and measure their speed and trajectory. Cameras capture visual data, enabling the vehicle to recognize signs, road markings, and traffic signals. Ultrasonic sensors measure distances using sound waves, assisting with parking and obstacle detection. Once the vehicle has perceived its surroundings, the next step is path planning. This process involves creating a safe and efficient route from the current position to the desired destination. Path planning algorithms consider factors such as traffic conditions, road closures, and pedestrian activity to determine the optimal trajectory. Decision-making is another crucial aspect of autonomous vehicle technology. It involves analyzing the perceived environment and selecting the appropriate action based on predefined rules and machine learning models. For instance, if a pedestrian crosses the path of a vehicle, the system must decide whether to stop or proceed while ensuring safety. Control is the final stage in the process, which uses the planned path and decisions made to execute the necessary maneuvers such as steering, acceleration, and braking. The control system works in real time, making adjustments as needed to keep the vehicle on course. The automation of vehicles is divided into 6 levels, defined by SAE International from level 0 to level 5. Each level represents a different degree of automation, outlining the capabilities and limitations of the system. Understanding these levels is essential for comprehending the current state of autonomous vehicle technology and its potential future developments. Level 0 is no automation, where the driver controls everything and the system can only give alerts like lane departure or collision warnings. Level 1 is driver assistance, where the system can help with either steering or braking acceleration, but the driver must stay attentive and ready to take over. Level 2 is partial automation, where the system can manage both steering and speed control at the same time, but the driver must continue monitoring the environment and take over instantly if needed. Examples include Tesla Autopilot and GM Super Cruise. Level 3 is conditional automation, where the system takes responsibility for driving under certain conditions such as highway traffic jams. The car itself monitors the environment, But when conditions go beyond its design, it requests the driver to take over. An example is Audi's traffic jam pilot under testing. Level 4 is high automation, where the car can drive itself completely within a defined area such as a city center or campus. If it encounters conditions outside its design, it can bring itself to a safe stop. Examples are robotaxi services being piloted by Waymo and Cruise. Finally, Level 5 is full automation, where the vehicle can drive in any environment and condition without a driver. Steering wheels and pedals may not even exist. At present, Level 5 is still only a concept and not commercially available. These levels provide a framework for understanding the capabilities of autonomous vehicles and serve as benchmarks for measuring progress in the field. As technology advances, we can expect to see vehicles reaching higher levels of automation, bringing us closer to the vision of fully autonomous transportation. To achieve autonomous driving, vehicles leverage a variety of technologies working in concert to perceive, navigate, and respond to their surroundings. One of the key technologies employed by autonomous vehicles is LiDAR, which uses light waves to measure distances and create detailed maps of the vehicle's environment. LiDAR sensors emit laser pulses and measure the time it takes for them to return, calculating distances to objects with high accuracy. Radar is another essential technology that utilizes radio waves to detect objects and determine their speed and trajectory. It allows vehicles to perceive their surroundings, even in adverse weather conditions such as rain or fog. Cameras play a vital role in autonomous vehicles, providing visual input to the system. Advanced computer vision algorithms enable vehicles to recognize signs, road markings, traffic signals, and other visual cues. Ultrasonic sensors use sound waves to measure distances over short ranges, assisting with tasks such as parking and obstacle detection. These sensors emit ultrasonic waves and measure the time it takes for them to be reflected back, providing information about the distance and location of nearby objects. In addition to these sensor technologies, autonomous vehicles rely on precise positioning systems such as GPS and inertial measurement units to determine their location and movement. These systems provide accurate positioning data, allowing vehicles to navigate roads and follow routes precisely. High-definition maps are also crucial for autonomous vehicles, providing detailed information about the surroundings, including road layouts, lane configurations, and nearby objects. These maps are regularly updated to ensure accuracy and are used by the vehicle's navigation system for route planning. Vehicle to everything. V2X communication enables autonomous vehicles to exchange information with other vehicles, infrastructure, and roadside equipment. V2X communication allows vehicles to receive important information such as traffic signals and hazard warnings, enhancing situational awareness and safety. As we delve deeper into the realm of autonomous vehicles, it's important to acknowledge the formidable challenges that lie ahead. While significant progress has been made, there are still numerous obstacles to overcome before autonomous vehicles can become commonplace on our roads. One of the primary challenges associated with autonomous vehicles is the complexity of real-world scenarios. These vehicles must be capable of handling a wide range of situations, from routine commutes to unforeseen circumstances such as inclement weather, construction zones, or unexpected road conditions. Developing algorithms and systems that can reliably navigate these complexities remains a significant hurdle. Safety is paramount when it comes to autonomous vehicles, and ensuring public trust in their reliability is crucial for widespread adoption. Addressing concerns regarding the safety of autonomous systems and demonstrating their ability to handle emergencies effectively is essential for building confidence among users and regulators alike. Another challenge is the legal and regulatory landscape. Establishing liability in case of accidents, ensuring data privacy and security, and defining clear guidelines for autonomous vehicle operation are essential for the smooth integration of these vehicles into our transportation systems. Collaboration between automakers, policymakers, and legal experts is crucial for creating a comprehensive framework that governs the use of autonomous vehicles. Infrastructure plays a vital role in the successful deployment of autonomous vehicles. The availability of accurate and up-to-date maps, reliable communication networks, and standardized road signs and markings is essential for seamless navigation. Investments in smart road technologies and connected infrastructure can significantly enhance the capabilities and safety of autonomous vehicles. The cost of implementing autonomous vehicle technology remains a significant barrier. Advanced sensors, computing power, and the necessary hardware and software components contribute to the high upfront investment required for these systems. Reducing costs through technological advancements and economies of scale is crucial for making autonomous vehicles more accessible to consumers. Overcoming these challenges will require collaborative efforts from engineers, policymakers, industry professionals, and researchers worldwide. By working together, we can pave the way for a future where autonomous vehicles enhance our lives, making transportation safer, more efficient, and more accessible for all. In conclusion, autonomous vehicles are poised to revolutionize the future of transportation, offering enhanced safety, efficiency, and accessibility. Through advancements in perception, path planning, decision-making, and control, these vehicles can navigate complex environments with precision and accuracy. While challenges remain in areas such as real-world scenario handling, safety, legal considerations, infrastructure requirements, and cost reduction, ongoing research and development efforts are paving the way for a future where autonomous vehicles become an integral part of our transportation systems. With continuous innovation and collaboration among stakeholders, we can harness the transformative potential of autonomous vehicles to create a safer, more efficient, and more sustainable transportation ecosystem for generations to come.